You're like, oh, I regretted that saying that. He's going to make me do more titrations in gravimetric. All right. So, EDTA titrations. I know the wonders of titrations. Now, titrations are incredibly useful for analytical because they're just very, very dependable, and you can basically make them as accurate and precise as you want to make them. If you use a lower concentration titrant, right, you can increase the accuracy and precisions. Okay. You also have to consider the matrix effects. Okay, so when we're looking at these titrations, what we're going to be looking at is what's called analytical complexation. For everybody who's taken inorganic chemistry, they'll remember complexation from that. For everybody else, you probably haven't really run across this much yet. Okay? And so complexation is taking an ion, typically, it'd be a cation, and you complex something to it. Okay, so hydration was making a complex of your ions with water. Okay. In this case, we're going to be making the ions with a ligand that's a very strong ligand, which is EDTA. Okay. Ligand meaning something that binds across it. This right here is the formula of EDTA, and that's what I need you to have in your head right now. Okay. Is that EDTA, this is the formula, see it has all these CO groups. Okay. And so these CO groups, they're going to bind across on this metal ion here, like so. Can everybody see that okay? And can you see how it looks a lot like a hydration would? Because they typically make very similar structures. EDTA in this case is a multidentant, meaning think of like a tiger pouncing and it bites in, right? That's what it's going to do. It's going to bind multiple places to whatever you're titrating in this case. Okay? To your metal ion. Okay. Now, the full name of this is ethylene diamine tetraacetic acid. It's going to compound. It's going to form 1-to-1 complexes with most metal ions. It's very unusual to find something that would form more than 1-to-1 complex. And so it ends up being incredibly useful for any quantitative analysis of metal ions. It's going to play a role as a strong metal binding agent, used heavily in all sorts of industrial processes, from detergents. They're selling you detergent right now today with EDTA in it. Okay? If you look at the back labels, you'll see it in all these sort of products. Cleaning agents, of course, food additives. They may know why you would have it in food. No? So metal catalyzed oxidation of food is actually one of the major sources of spoilage. Yeah. So if you ever notice, you can prevent a lot of the spoilage and browning, right, by taking like meat and putting them in vacuum bags, so you get rid of the oxygen. But you can also do that by getting rid of the metal ions. Okay? And so you can greatly hinder spoilage. Right? And it is safe to eat a fair amount of this, so of course you can get poisoned by anything. So yeah. Don't go to the lab and like especially the EDTA we have in lab is going to be pretty basic. Okay? We're typically going to work on it with that in like pH 10. Okay, now this is actually one of the few ways that you can deal with most radioactive metals, in case you're wondering. So if you ever get radioactive poisoning, they typically give EDTA to attempt to flush it out before it can kill you. Okay? It's one of the ways you can do that. You can also use iodide to try to bind it and remove it from your system. Alright, so let's talk about metal chelate complexes. So metal ions are going to be Lewis acids, accepting electron pairs from the electron donating ligands, which are going to be the Lewis bases. Remember, ligands are going to be the things that bind to them. Okay? Now, monodentate ligands are going to bind to metal ions only through one atom. So this is a monodentate ligand. In this case right here, we have the silver metal right there, Ag+. These cyanides are going to bind to it. See how it only binds one time here. on that carbon there. That's monodentate. Monodentate, by the way, meaning bite, teeth. Okay? So it bites once. Right? Okay. Multidentate, these are typically referred to as chelating ligands. You can use either terminology, but chelating is usually the more popular term. But multidentate, multi-biting, right? They are going to bind more than once. And so they're going to bind through more than one atom on the ligand. So here we have copper 2+. It's going to have this bidentate coordination, meaning it binds on 2 of the atoms in the ligand. Okay? Everybody got that part so far? Okay. Anybody know why it's coordination, by the way? My organic person. The electrons are coming just from the nitrogen, right? So it's a coordinate reaction step. Okay, so right here, let's talk about the chelate effects. So the ability of multidentate ligands to form more stable metal complexes than those formed by similar monodentate ligands is the chelate effect. That's why they're calling chelating agents, is they can form more stable complexes than your typical monodentate. Probably the most common monodentate that you'd have to worry about and talk about is water. Like we were talking about, the hydrated ions are monodentates binding to the cations, right? So that's all that ever was. So again, right here, we have a reaction. We have the water, the hydrated version of that metal ion. We put in a bidentate right here, multidentate chelating agent. And it's going to bind on 2 spots for each of these atoms instead of 1, right? And it'll bind like this. And see, so it displaces 4 of the waters. Okay. Does anybody know why it wouldn't bind the last set? It just can't stretch. They're on opposite sides of the metal ion, so it can't get to the opposite sides. Okay. Again, this right here would be ethylamine. This would be methylamine right here. This one right here is actually a monodentate. And so what we can see here is we'd actually replace singular ones of these to make our product. Now, if you look at these formation complexes, complex formation equilibriums, what you see here is this is 1,000 times more likely to occur than this one, right? So you'd end up with 1,000 times the concentration of this versus this if everything else was equal, right? Okay. Can everybody see those from these K values right here? Okay. Is everybody comfortable with the fact that these are betas? What does that beta mean? It's because it's forming a complex, right? So it's going to form that complex. That's beta is just another way of referring to a K for a complex. Okay, now let's talk about ATP. This is a tridentate ligand. It's actually going to bind divalent metal ions, so things like magnesium 2+, manganese 2+, cobalt 2+, nickel 2+. The biologically active form is actually the tridentate form right here. And so it's going to typically require magnesium 2+ to be biologically active. You can't actually usually cleave this and generate energy in a biological system without your magnesiums. That's why you get all these products sold to you, magnesium breakthrough, blah, blah, blah. Okay? Is you actually need that for you to produce energy and use your energy. Okay? Anybody confused there at all? Did I lose anybody? Fantastic. Okay. So, I'm going to skip some of this biological stuff because we really need to try to make some time. Now, these right here are some common chelating agents. You'll notice the EDTA right here, but there's other ones other than EDTA. Okay? And so these are the most analytically useful chelating agents typically that you would find. All of these are multidentate, and they are very, very strong formation complex K values. Okay? And so they're very, very large ones. So they mostly are going to bind whatever you put with them. Okay? Now, this is the amine nitrogen atoms and the carboxylate oxygen atoms. These are all potentially ligand atoms in these molecules. And so any of those points where you see a lone pair on a nitrogen, lone pair on a carboxylate, those are all going to be potential sites to form your complexes with. Okay? So those are potentially your dentates. Okay, so complex symmetric titrations are going to be based on metal-ligand complex formations. Ligands are going to form strong one-to-one complexes with all metal ions, the exception being the univalent ions, which would be lithium, sodium, potassium. Okay? And that's because of the charge and the size. So the stoichiometry is going to be one-to-one regardless of the charge on the ion, because they're going to wrap around those, and thus it will hinder anything else from trying to bind to it. Okay? That's the part of what's magical about these multidentates. I know, you were saying you wanted to go back to stoichiometry. Look at that, we didn't not take long, did we? Now, EDTA is by far and away, from what I've seen, the most widely used chelator. I would say something of like 90% of chelating is done using EDTA. Okay? The other ones are just minuscule amount of the chelating agents compared to EDTA. They do have uses, sometimes important uses, because they're, the minutia does matter, right? If we learn one thing from chemistry, small things matter, don't they? Okay. Now, direct or indirect titration, you can do it either way. Virtually every element on the periodic table can be measured with EDTA titrations. And so if you're clever with your EDTA titrations, I'm going to give you a technique right now that's like your hammer or your screwdriver, right? That if you're clever with it, you can use it for every job. Okay, there is no job that you can't do with EDTA in some way, shape, or form. Okay? Is it going to be the best option always? No. No. But if you can't figure out another tool, EDTA titrations, either by forward titration, direct titration, or by indirect titration, will work on almost everything. Okay? It's very rare you would ever encounter something you just cannot measure at all with EDTA. Now, does everybody remember what direct versus indirect means? Direct titration is like, I add NaOH to an acid, and it directly reacts, right? So indirect titration is where I have an ion, it binds to something, and then that released ion is what I then test against, right? And so that would be that last titration we did with the superconductors, right? We were indirectly measuring our superconductor. Okay? Okay. So EDTA, this is a hexaprotic system. It is designated as H6Y2+. Okay? And so it is hexaprotic. It is a, hexaprotic titration if you were to do the most acidic form to the most basic form. You typically don't have to worry about all of that, but that does mean your concentration of any single form changes as your pH changes, right? Okay. So the neutral acid is actually tetraprotic. It'll have the H4Y. This would be the neutral one. Again, notice the 2 plus, right? We get rid of 2 H pluses and go to the neutral. Okay. These are the different pKa's. Notice the first pK is really, really, really low. You have to get very acidic to get that. Okay. That's like you've added concentrated hydrochloric acid to this stuff to get there. Even the second pK would be considered very low. The third pK is also quite low, right? So you don't have to try hard to get to the neutral H4Y form. Okay. This right here is actually the different fractional compositions designated by the pH. And what you notice here is when you're acidic, you have a lot of different forms, right? As you get more basic, you actually start separating out the forms more. Okay? Okay. And those are the ones you start looking at these nitrogens, right? At the end. Those are the pKa5 and the pKa6, i.e. the ones that you'd have at like pH 6 and pH 10, right? Okay. Can everybody see okay? That's the majority of what you actually would want to use, is this stuff over here. Because they have all the dentate regions, right? Remember, your carboxylic acids are the majority of your dentate regions. Okay? They're going to act as the multidentate and do your best binding. Okay. Now, that will actually change your properties of your binding. So if we were to look at the fraction of EDTA in each of the forms, this is actually the equations we would get for these. Okay? And so if you were to do it every single form listed out, this is what that looks like, right? All the forms listed out, and then we have the composition, the fraction of the Y4 minus form, divided by all the forms. This can be summed up as the formal concentration down here. Okay? And so that's just the formal concentration down there. It's all the different forms, right? Now, you can actually rewrite this like this right here, which is the Ka1, K2, K3, K4, K5, K6 over the D. D would be this terms right here. Everybody recognize that? Remember when we were talking about the triprotic and then more protic acids going past that? This was that equation that I had listed out, and you have to do the repeated pattern down here. That's that one. Okay? This is just done the repeated pattern from that. Right? So this is that repeated pattern that you would have to actually generate. This is it for a 6-protic acid. Hexaprotic acid. Now, this right here is the values for the fractional compositions at different pHs at 25 degrees at ionic strength of 0.1 molarity. Notice 0.1 molarity ionic strength is very common ionic strength to be at whenever you're running experiments. 25 degrees Celsius is the standard room temperature, right? And so this is like your handy-dandy table that you can reference when you try to do these experiments. Okay? So if we look at this, what do you notice about the concentrations of the Y4 minus, which is the deprotonated form? What happens to it as you go up in pH? It goes up, doesn't it? Okay. Why does it hit 1? What does 1 mean? All of it, that's all the DTA would be in this form, right? The Y4 minus, the fully deprotonated one, and the one with all of the dentates available to bind to a cation. Okay? And so this right here is the form that is the most effective multidentate. It is the one with all of the sites available to bind. So it's fully available to bind. It can do all the binding it can do. Okay? Now, if you're at 1 for this, this is going to give you highly uniform binding characteristics. Okay? If you're at 12, 11, you're going to have less of it available, right? And then at 10, you're going to only have about 30% of that available as that form, right? Everybody see that okay? You understand how to read that now? Okay. So, again, let's talk about that fractional composition, right? So, alpha, fractional composition. Now, the fraction of all free EDTA in the form of the Y4 minus, that is alpha Y4 minus, right? So at pH 6, you'd have formal concentration of 0.1. Your composition of EDTA would actually be like this. If you're wondering where you would get this, you would have to do the calculations we had talked about. Remember doing all the intermediate form concentrations with the calculations for the diprotic and triprotic? just be those problems like we did before. Or you can have a graph like this and you can actually reference the graph. Okay. All right, so these are the concentrations right here. And what do you notice about these concentrations? Well, the majority of this species right now is in the Y2, H2, Y2 minus, and the H3, HY3 minus. Man, I'm tired. Really need to get coffee in between these classes. Now, how would we find the fractional composition of the Y4 minus? Using this data right here. What's fractional composition again? It's the amount of the one you're looking at, right? Divided by all the other amounts added together. So the formal concentration, right? Which is all of them added. Yeah. So if you just add everything up together, then divide this by that number, you'll get your fractional. Maximum you can ever be is 1, right? Okay. Now, one of the things I should point out here, do I actually have to add that number right there? No. No, I don't. Yeah, I can just take this number, add this number, and I'm pretty much good. All right. Yeah. Any other numbers, I just end up rounding off. Okay. So that's one of the ways you can make yourself go a little faster when you're doing these calculations, when you're doing homework, when you're doing tests. Okay. You don't have to add every single number. All right. So if you go ahead and do the math problem, this is what you'll get. It's 1.8 times 10 to the negative 5. Okay. By the way, interesting little factoid is they did give you the formal concentration right here. So you could have just done the formal concentration if you were given it and put that in. So, but again, if you're not given the formal concentrations, it's each of the amounts, right? Which is the definition of the formal concentration. Now, the formation constants, or stability constant, is typically labeled as Kf. K is in equilibrium, F as in formation. So again, that's going to be your equilibrium constant for the metal ligand formation reaction. Okay, that's just this reaction right here. So the Kf for EDTA is going to be defined in terms of your Y4 minus species reacting with the metal ion. Does not mean that the Y4 minus reacts with metal ions that only the Y4 minus would react. Okay? If you have the Y3 minus, the Y2 minus, the Y1 minus, even the Y would react to some degree and be a ligand. Okay? So all the forms can act as ligands to varying degrees. The Kf for most EDTA complexes are very large and tend to be larger for more positively charged ions. So the more positively charged this ion is, the larger that formation complex typically is. These right here are the logs of the Kf. Notice these are pretty dang big values, right? Mostly across the board. There's a few spots where they're not that large. What do you notice about the spots where these are not very large? Yeah, the singular cations, yeah. Especially the ones on the top left, right? Real small, so you can't actually wrap around it. It's so tiny, right? And it only has 1 plus charge. Yeah. Okay, and so again, EDTA, hexadentate ligand, it's going to bind the metal atom from 6 ligand bonds. You'll notice for most formations, that's actually filling up the majority of the spots on the metal cation. Okay? So in many transitional metal complexes, the EDTA actually engulfs the metal ion as a 6-coordinate species, like so. Now, this space-filling model actually implies the 6 coordinate strains of the chelate ring this strain can be relieved by distortion of this. Distortion actually opens up a 7th coordination site, which can be occupied by the H2O right here. This is distortion, by the way. See how it's distorting from the normal patterns you would see around this ligand? Like it's not up cross like we saw in a lot of the other previous ones. And so you can get water bonded to these because it'll be energetically favorable to bind that extra spot on the EDTA and relieve that ring strain. Now, formation constants are going to describe this reaction right here where we're forming the complex with the EDTA for minus. Below pH 10.37, most EDTA is not the Y4 minus if we looked at our table from before or our figure that we looked at the concentrations, the fractions. So the concentration of Y4 minus can be expressed as Y4 minus concentration equals mole fraction times the formal concentration of EDTA. Notice again, the fraction had formal concentration on the bottom anyways, right? So, okay. This right here would be the rearrangement where we plugged in this relationship we just talked about down here. Okay? And so you can figure out, using the formation constant, the complex concentration up here, the concentration of metal line down here, this is the fraction right here, and then that's the total concentration of EDTA. Now, there is a conditional formation constant or effective formation constant, which can be summed up as K prime F. And what that is going to be, it's going to be the equilibrium constant at a specific pH. Okay? So at that pH, it's not actually changing your actual KF, but it's effectively changing it because you have less EDTA to work with, right? And so this right here is your value, your K prime F equals your mole fraction. See, that's the only term we changed here. So we take that in front, times your KF in the table up here. Okay. Where do you get this value? pH. You look at the pH, you compare it to the table, typically, unless you are divergent from those conditions considerably. Okay? This right here from the table right here, right? Plug those in, you get the K prime F, which you can then solve concentrations just like you did normal equilibrium problems, right? And so we've just wrapped back up into our normal equilibrium problems. Go ahead and try it out real quick. By the way, you oftentimes get to kind of decide your concentrations for things. So one of the things you'll notice is that concentrations are typically set in these experiments as something 0.1-ish. Because you want the ionic strength to be 0.1-ish. So you can just use the table to figure out your composition of EDTA. Okay. Everybody got a good solid start? Okay, we'll go ahead and work on the rest of it together. So this is our reaction right here, right? So we have our EDTA binding to that. What we need to do is get these values from the table for pH 10 and pH 6. And then we just need to plug it into that formula to get K prime F. Okay? And so we look up pH 10, it's 0.3. By the time we're done with this, by the way, you are probably going to have that number memorized. the 0.3. Even after all these years, I still have it memorized. Yeah. And so 0.3 times that 10 to the 10, 0.65, which is that value right there. You look up the pH 6, that's 1.8 times 10 to the negative 5, and so you get your K prime F right there. Okay. All right, so the next thing you do is you just do your normal equilibrium expression that you would normally do the calculations for. And so what we see right here is we have a formal concentration of 0.1, right? This is minus X because you're using this top one up. And then on the bottom, you have these concentrations, which would be equal. Okay? This is going to be equal to the K prime F. And then you just solve it for each of these. Okay? So if we go ahead and solve, at pH 10, what you would find is 2.7 times 10 to the negative 6. At pH 6, you would solve, and you'd find 3.5 times 10 to the negative 4. Now, one of the things I would like to point out here is that you are always on these EDTA titrations going to be very large values here. Okay? And so one of the things you do have to watch out for here is that this top number is usually way, way bigger than this bottom number, right? Everybody understand that okay? Because your values are like 10 to the 10, 10 to the 5, that sort of stuff, right? So, and these values are usually like 0.1, 0.05, okay? And so if you actually pay attention to these, you can usually not bother putting an X here. The minus X here. There's almost always something minuscule, right? Does that make sense for everybody? So these are really, really good problems to assume that they're going to be 1%. And then come back and was it 1% or less? Okay. They're usually like 1/10,000th. So it almost always works out. Now, let's talk a bit more about the pH effects of this titration curve. So again, what did you remember about your concentrations? If you have very low concentrations, what happens to your titration curve? High concentrations, very distinct titration curve, right? Low concentrations, what happens to your titration curve? Flatter. And so because our concentration is directly tied into pH, pH is going to flatten our titration curve. Okay? So if you have lower pHs, your curve is going to flatten. After pH 6, I won't even try to do that. It's going to be very difficult. Okay? You really have to set situations up to be incredibly young. So it's typically like 5.5 is the cutoff where people would just go, this is not really going to work. It's not going to give you an accurate determination. Up to 5.5, if you're incredibly careful, you can get useful data. Most people do this at like pH 7 and up. Okay? Why would you not use pH 12 for everything? What happens to like pH 12 to, let's say, U? U turn into soap. And so, if you're trying to titrate something, it's a little problematic if it reacts with OH minus, right? Yeah. And so that's not uncommon for things to be very reactive in strong bases, right? And so it's one of the reasons why you would do things at pH 9, pH 10, pH 7, right? It's because it'd be reactive. Okay. So 3 regions of your EDTA titration curve. They're the same sort of 3 regions we had talked about before. This would be very similar to like a strong acid, strong base titration, okay? And so you have before VE, this is going to be excess unreacted metal is present, and this is going to be determined by the excess unreacted metal that's present, okay? And so this would be that minus, like we were doing for the strong acid, strong base. Then we're going to have VE, so there's going to be exactly as much EDTA as the metal in solution, And this is going to be determined by your dissociation according to that K prime. Okay? More often than not, that K prime is going to be massive. And so you're going to have very tiny numbers. Okay? They're almost all going to be bound as complex. After the VE, your excess unreacted EDTA will be in solution. And so you'll have to use that excess EDTA in your K prime F. Okay? Don't forget, you're going to be, even if it's only 30% of that EDTA, as in the fully deprotonated form that binds, you're still going to be increasing that amount, right? If you keep adding more. Okay? Okay. So you're going to have to use that in your expression to calculate the metal that remains unbound. All right, so let's go ahead and try it out. Here we have before the equivalence point. So we have a titration 50 milliliters of calcium 2+, which is 0.04 molarity. It's buffered at 10 milliliters. Typically, you're going to use some form of buffer to keep your pH constant. Otherwise, you're going to have your EDTA concentration swing around as you're doing these titrations, and you never know where you are. Okay. By the way, have you guys seen Tris buffer recently? That's what Tris buffer is typically used. A very, very common buffer used in these systems. Now, you're going to have the 0.08 molarity EDTA. So again, we have the pH 10. The alpha for that Y4 minus is going to be 0.3, right? 30% of it will be in that form. And so we multiply our Kf, which is 10 to the 10.65, and we get our K prime F, which is that way right there. Okay. Okay, this will be needed later. For this first part, you don't really need this. The first part, you just straight up calculating how much calcium 2+ you have remaining, because EDTA binds very well to calcium 2+, right? So, you're going to take, you have 25 milliliters, right? You're adding 5 milliliters of EDTA, so that's minus 5 milliliters of the EDTA. And then that's over 25 milliliters right here. This is your fraction that remains after you would get to VE. Okay. Is everybody comfortable with that so far? Everybody understands how to get to V, how to calculate V's. Nobody's struggling with that anymore. Okay. If you are confused, let me know. Okay, so you're 1/5 the way to the V, right? And then you're going to use the original calcium concentration, and now you need your dilution factor. Yeah. So your 50 milliliters you start with, 50 plus the 5 you added, right? That's dilution. You get your concentration. More often than not, you would represent these as P calcium, P lead, P whatever, which is negative log of those concentrations, right? So you take the negative log of that, and that will give you that concentration right there, 1.54. Okay. And that's going to be your largest concentration that we do at these problems, right? Okay, so the next part, we're going to get the equivalence point. So at that point right there, at the equivalence point, virtually all of the metal is going to be in the bound form. And so that calcium Y2 minus is going to essentially be equivalent to the concentration of the calcium 2+ corrected for dilution. It's going to be the vast, vast, vast majority of that concentration. How do we know that it's going to be the vast majority of that concentration, by the way? This value. See how large this value is? So if we are at the equivalence point, we're going to expect whatever concentration we end up with the complex to be something like, what is that, 1,000 times a million times 10? Concentration difference, right? Massive number difference. And so it's almost all going to be the complex. So again, we have the concentration of your calcium. It's going to be the initial volume of your calcium divided by the new volume, which is, again, that's the dilution factor. Again. And so that gives us our concentration of our calcium Y2 minus. Now, if you stopped here, your concentration of free calcium 2 plus, well, it's a small number, but it is a number, right? You do have some calcium 2 plus, okay? And so currently it's unknown. We needed this value to be able to do the equilibrium work, the equilibrium expression, like we normally would do. And so this is going to be what you have to plug in, okay? So you do your formal concentration of that complex, which is the number we just got. It's going to be minus x. That's the stuff that comes back apart. And then you do over x squared. Everybody recognizes that formula, okay? Okay. Everybody see that we're just doing this backwards because we're a formation constant instead? It's very similar to the work we did with acids. Okay, so we set that equal to the K prime F, which is this value here, the 1.34 times 10 to the negative 10. Again, because this is such a small value, by the way, you can very comfortably ignore this minus x value here and just double check that's less than 1% of this value here. Okay. We solve that, we get 1.4 times 10 to the negative 6. Notice that is less than 10% of this, or 1% of this, right? So it is much, much smaller, so that assumption will be good. Okay, and is everybody okay with assumptions and where to make them? You understand it? Come on, let's stop talking about it. But no, I probably made the assumption. Okay. Now, again, we'll take that concentration of calcium, we're going to put it at negative log, and that's going to give us the P calcium. And notice, again, it is a very, very tiny value. Most of it has been complexed. Okay. Region 3, this is going to be after, so we're adding additional EDTA. And so whenever we do this, we just need to increase the amounts of EDTA that is effectively in that system. Okay? What that means is the K prime is what we're going to change. All right. So we take our concentration of EDTA here, right? See that? And this is going to be the volume of the excess EDTA over its dilution factor, right? Okay. This is going to give us our effective concentration of EDTA here. Okay. Okay. So again, we plug these in. So this would be your equilibrium expression, right? And we have the calcium concentration, this complex concentration, which is the number 2.63, is that 0.0263 number we've been using. Essentially the formal concentration of calcium. Because almost all of it will be complex. We put our concentration of our EDTA right here, and then we just solve for calcium 2 plus each time. Okay, and so that's going to give us this new value right here for calcium 2 plus concentration. Note that you do have to be careful. This value for the calcium bonded to the EDTA, this can change depending on how much you increase your volume, right? So in this case, it looks like almost the exact same value here, but that's because we only changed it by 1 milliliter out of 75 milliliters, right, or 76 milliliters, excuse me. So, this would be how you calculate that concentration. Again, it's just the original concentration times dilution factor. Anybody have any questions? Yeah, it's just the same step down here as well. You'll notice that, again, these titrations are extremely similar to the strong acid, strong base titrations. The only caveat is that EDTA is not a constant concentration. That if your pH is different, you're going to have different concentrations for it. You need to account that for your K prime. Okay, so this right here is going to be your titration curve. Again, notice we have the large formation conditional formation constant. So the larger this formation constant, the more distinctive this inflection point is going to be, and the more easily it's going to be found. Okay. Typically, EDTA titrations will have a very distinct point right here. If the pH is lowered, your VE is going to become less distinct. If your concentrations go down, your VE is going to become less distinct. The pH cannot be raised arbitrarily high because, again, metal hydroxide might actually precipitate. And so many metals, when you're trying to measure them, will react with hydroxides. For example, lead reacts very strongly with hydroxides, and so this becomes kind of difficult to do, actually, with lead solutions. Yeah. So you do have to watch out for that. This is actually how you do it in a spreadsheet. I would actually try it out in a spreadsheet when you get a chance. It works quite nicely, actually. Okay? And it's good to learn how to use spreadsheets. Though it's something that you really need to try, and then you can come in and go, I don't get what I did wrong. Then we can go through. Now, let's talk about auxiliary complexing agents. So EDTA titrations were selected to prevent metal hydroxide precipitation at the chosen pH. To permit many metals to titrate in alkaline solutions with EDTA, we oftentimes use auxiliary complexing agents. And so an auxiliary complexing agent is going to be a ligand that binds to the metal strongly enough to prevent the metal hydroxides from precipitating, but it's weaker than EDTA. Okay? You may have noticed some of these that we had started talking about a little bit. One of the major ones you'll notice is citric acid, actually. Anybody notice you look at the back of your soda or whatever you're drinking, Powerade, whatever, and it says like citric acid, EDTA. Guess what they're doing? They're doing the same sort of chelating behaviors. Okay? It's kind of an interesting thing that it's actually widely used. Now, so again, it has to be a happy medium between, it has to be a stronger chelating agent than hydroxide, but it has to be a weaker chelating agent than EDTA. Okay? So strong enough that hydroxide can't precipitate it, weak enough that the EDTA can strip it. So let's consider this one right here. Here we have a metal ion. It's going to form two complexes with our auxiliary complexing ligand. It'll have the ML, and it'll have the ML2 form. Okay? And these right here would be those expressions. So our cumulative formation constants can actually be arranged, rearranged, and we can put in a mass balance equation, and then this will give us our free metal ion that is available. So our free metal ion would be this if we were to write it out fully. But if we go ahead and solve for it so we can more easily do the math in the future, we would get this form right here. Notice what is not in that form for our metal ion concentration fraction. Is there any metal ion concentration? Not at all. So the thing that our metal ion composition does not depend on is concentration of the metal ion. Okay. It is, in fact, independent of the composition of the metal ion because it's a fraction that's available. Notice again, these are just the formation constants here, and this is the concentration of your ligand. Okay. All right. So this right here would actually be an example. I'm just going to go straight through to trying it with y'all. So we have zinc 2+. It's with ammonia. It forms these complexes right here. If the concentration of free unprotonated ammonia is 0.1 molarity, find the fraction of zinc in the form of zinc 2+. At any pH, there's going to be some NH4+ in equilibrium with the ammonia. So, how we're going to do this, we would have to go to the appendix. We would have to find the formation constants for all the possible forms we just were shown. Okay? So we look at our appendice, and we find complexes. These are our complexes. That's the formation right there, constant. This is the complex, formation constant, and so on. Okay? We have all of those values. The other thing we need is the formal concentration of ligand, right? Which we were given in the problem. So that's, in this case, it is going to be 0.1 molarity, right? So what we do now is we take this, and we're going to go 1 on the top, divided by 1 on the bottom, plus the first formation constant, times the ligand concentration. Second formation constant, times the ligand concentration. Why is this 1, 2, 3 like that? Why does this number always seem to match this? How many NH3s are there here? 1. 2 here, right? 3 here. Okay? And so where do these powers come from? The coefficients, right? So that's just the number of ligands that's attached to each of those metal ions. That's where you get that number there. Okay? Is everybody okay with that so far? All right. You do the math. Always do the bottom first, by the way. If you try to plug this all in one go in your calculator, it will get messed up. We get this value here for that composition of our free zinc 2+. So what we see is in the presence of 0.1 molarity in NH3, the amount of zinc 2+ available in that solution is going to be extraordinarily low, right? The vast majority is going to be bound to the ammonia. Okay, let's go ahead and consider this titration of zinc 2+ by the EDTA in the presence of our ammonia. So if we were to extend our calculation, our equation 12.6, and we put in a new conditional formation, so we have a K prime prime, double prime, because we have another condition that we added for that formation complex formation. It's going to be equal to the fraction of zinc 2+ that's available times the fraction of the EDTA that's available in the 4- form times the KF, right? So it's going to be how much of each of those is available times our KF. Notice we've just added the zinc 2+ portion here, haven't we? Okay, so the K double prime F is going to be a conditional formation constant. It's going to be at a fixed pH and fixed concentration of the auxiliary complexing agent. If you were to add more ammonia to this, you would have a different one, wouldn't you? Okay, because you would have a different amount of zinc 2+ that would be free at that concentration. So, let's, one of the assumptions that's in this calculation that makes this work is that EDTA is a stronger complexing agent than ammonia, so that essentially all EDTA binds to zinc 2+ until your metal ion is consumed. If it is not significantly stronger, like hundreds of times stronger, this is not going to work. Okay? No, metal ions are going to react with water. They will form the metal OH species, which is the hydroxide ion species, and the water hydrated form. The conditions, low pH, this does not occur. So you're going to find more of it as the M2+ form at lower pHs. The M3+ and M4+ forms are going to form hydroxides. Even in acidic solutions, it's one of the reasons it's very difficult to get things like an iron 3+ or lead 3+, 4+, and do these things. Even at acidic conditions, a lot of the lead would actually be in the lead hydroxide. Okay. Conditional formation constant for Fe3+ actually has to become this right here. Okay. Notice the triple prime now. And we actually have to take into account the amount that's going to be the Fey form. Okay. So in this case, we actually are going to have this decent amount of the Fey form. So This is going to restrict discussion to cases where there's no hydrolysis and the alpha Mn2 plus is controlled by deliberately adding auxiliary ligand. The metal has to be deliberately controlled with auxiliary metal ligand. Okay, so let's consider our titration. We have 25 milliliters of 1 times 10 to the negative 3 molarity zinc 2 plus. We're going to do it with 1 times 10 to the negative 3 EDTA. The pH is 10, the presence of 0.1 molarity in H3. Again, note that this concentration, there is NH4 plus in the solution. The equivalence point is going to be 25 milliliters, and we're going to find the negative log of the zinc 2 plus. After the additions of 10, 25, and 30 milliliters of EDTA. Okay, so it's the same sort of formatting of problem that we just did before, right? Now we've just added every single factor into our equations. Okay? Okay. So the first thing we need to do, and the first thing you always want to do, is you want to find out your modified Kf. Okay? This is going to give you a lot of hints about your problem. For example, if it's a large value, then you can ignore parts of the problem, right? You don't have to do all the math. Okay? Now, the Kf modified one for all of these conditions is going to be the fraction of zinc 2 plus times the fraction of Y4 minus times the Kf. Okay? If we take our problem that we just did before, then what we're going to find is that it would be 1.17 times 10 to the negative 5 for that zinc 2 plus. That's that one we did before. Then we look up at our table, and we see that at pH 10, we're going to be 0.3 for the EDTA. And then we multiply that by the value from the table for the Kf. Don't forget you have to do it for zinc 2 plus. You can't just do it for random metal. Okay? We do the math. We get 1.1 times 10 to the negative 11 to 10 to the 11th, excuse me, not negative. So when we do this problem, we have 10, 25, and 30, right? We've been told the equivalence point's at 25. So what three regions do we have? 10 is before the equivalence point, 25 is at the equivalence point, 30 is after the equivalence point, right? Okay, so the 10 one is just going to be a simple problem where we take the concentration of the zinc 2 plus, and we're going to have to do the fraction that's remaining times the original concentration times the dilution factor. Okay? So this right here is your fraction that's remaining right here. That is 15 of 25. Notice that's the 25 you started with minus 10, right? Up here. This right here is the equivalence point, right? Okay, so we're 10 milliliters towards the equivalence point, right? 15 of 25 towards the equivalence point total. We used up 10. Okay, now the next thing we're going to do here is we're going to take the original zinc 2 plus concentration. This is just that total concentration not bound to the EDTA that we use right here. The next thing we have to do is we have to do the dilution factor. And so the dilution factor is going to be 25 divided by 35, because we added 10 milliliters. And that gives us the concentration of zinc 2 plus. Now, a little bit of a reality check here. Does this actually make perfect sense? Is it all actually zinc 2 plus? No. No, it's not all zinc 2 plus, right? Okay. Remember that when we're actually looking at the zinc 2 plus, in reality, the majority of that's probably bound to NH3, right? And so if we actually want the concentration of the free zinc 2 plus here, that's actually going to be zinc 2 plus concentration that we got just now, times the fraction. So we take the value we just obtained, right there, right? 4.29 times 10 to the negative 4, and we multiply it by the fraction of the zinc 2 plus that we got in the previous problem. Okay. And so that's going to be the actual amount of zinc 2 plus that's actually free in this solution. We take the negative log of that, and we get our value. Now, a little bit more of a reality check here. The zinc 2 plus and the hydroxide ion is actually going to have a little bit of formation as well. That's going to be like a 10 to the negative 16 amount. It's not really going to affect anything here. You would subtract it and it wouldn't be meaningful. But there are other forms. It just does not exceed the solubility product in appendix F. And that's how you'd actually have to figure that out if the hydroxide would be a meaningful amount. Okay. So once you're at the equivalence point, again, you're just going to plug these numbers into the equilibrium expression, right? And so you plug your concentrations into the equilibrium expression. Again, right here is the zinc bound to the complex. Don't forget you need to take into account your dilution factor, which is 25/50, right there. This is then going to plug into that same normal concentration minus x over x squared that we've been doing for all those times. We're going to use the k double prime f we got at the very, very beginning, right here. And we'll solve. And that's going to give us the concentration of the zinc 2 plus. Notice again, because we're doing this in a solution that has not all of the zinc 2 plus we're reacting was actually free at the beginning of it. To get the actual free concentrations of zinc 2 plus, we have to take that same fraction number we got at the very beginning, and we have to multiply it by those concentrations we get each time. Okay? And so that's going to give us the concentration of actually free zinc 2 plus. Okay. Everybody go ahead and work on the next one yourselves. Let me know if you have any questions or concerns or comments or don't understand something. I'm probably going to use that as my problem next time.